I'm gonna put a new one that's different than the one we had the other day. We're gonna do 2 recursively defined sequences. I'm gonna put a third one up that you don't have to memorize anything like that. It's just an interesting one. I want you guys just to know that. But so wait, memorize these? No. Every time you have recursively defined
Quickly
sequence,
recall.
it gets its own sequence. Okay, so I'm gonna put an example. Now for the second example. The third one is just a very famous one. When I put it up there, some guys will recognize it. Okay? Thanks, Bruno.
5, 6, 1, 2, 3, 4, 5.
I mean, I was thinking it right.
So like on this,
I don't think you were thinking of
Nice,
that.
quiet.
on a tester quiz, for example, you can give us like n equals 2x squared minus 5, and then we have to put in.
Oh wait, we already started
Those
taking
are
notes.
just the regular sequences. That is a formula for a sequence. So if I give you that and I say, give me the first 5.
Water bottle
put it like
There's
this.
no like set formula, right?
For those, every formula is different. Every time I do one, I can make it another one. Look here, 5n cubed minus 7 over 3. There you go, that's a mean. That's a formula. Then you just plug in 1, 2, 3, 4, 5, and you get the sequence. Okay? Now, the recursively defined ones, those are the ones that in order to find the terms of the sequence, you need to know the previous terms. Okay? So, first thing, they have to give you at least the first term. Sometimes they give you the first, sometimes they give you the first 2, sometimes they give you the first 2 or 3. Okay? I'm going to start with just one term instead of giving it. Now what they're going to do after that is they're going to give you a formula to show how each term is related to a previous term. So they're going to give us a list of it. AK plus 1 is equal to 3 times AK.
What is K?
Now K just refers to the number of the terms. I notice here's 1. So when K is 1, you're referring to the first term. When K is 2, it's the second term, and so on. Now when K is 2, this would be the second term. But if K is 2, that means that this would be the third term. Implying that to get the third term, I need to use the second term, which is why we call it a recursively defined sequence. It works kind of like on a loop. As I get answers, I can spit out the following answer.
I know
I
it.
get the next answer, I can come up with the one after that. So I know the first one. So if I know the first one, I can find the second one. So the second one would be 2 times the first one plus 3. So this would be 2 times, which is what? 11. Okay, everybody see that? Okay. So if I want to find the third one would mean, notice if this is 3, that's because K is 2, so it would be 2 times the second one. I already know what the second one is. So it would be 2 times 11 plus 3, which would give us 25. Now we're going to go ahead and go to 5 terms, just like we've been doing. You can do this as long as you like. We're going to do 5 just for practice sake. So if I want the 4th term, I'm going to multiply the 3rd term. Well, this is 4, that must be 3. Something plus 1 is always more than the previous term. So it's going to want to be 2 times 25 plus 3, which is 53. And over here, the 5th term. So it's going to be 2 times 4th term plus 3.
Teachers, please pardon this interruption.
Yeah, 1 and 9.
Pablo Hernando, please report to the attendance office. Thank you.
All right, everybody see that? All right, Larry.
Is there a way to find like the 12th term without having?
Okay, good question. That's exactly what the very next thing I was going to say. Now, you're doing it recursively. Realize the only way you can get a term when you're working recursively is by knowing what happened immediately before it. So the only way, if I'm working recursively, that I can get the 11th term is if I know the 10th term. I can't get the 11th without the 10th term. All right. The previous ones, the one we learned a couple days ago, when they give us a formula, they tell us find the 20th term. We're like, all right, I'll plug 20 in. Okay. Now, for some of these, once we create the sequence, and notice I do have a sequence here. Sometimes, by looking at the sequence, we can come up with a formula. Sometimes we can, but sometimes we can't. In fact, when we get to Tuesday's class, when we start dealing with these things called arithmetic sequences, we're going to look at the sequences in the form of formula, and we're going to look at them recursively. And we're going to see how those, when they're defined recursively, we'll be able to come up with a formula, so we won't have to deal with it recursively. That doesn't always happen. Like this one here, there might be a formula there, but that's not one that's easily found. Okay? So, we have to, if I want the 12th term, I'm gonna have to do this 7 more times. Yeah,
Are recursives always gonna have a k plus 1 or a k plus something?
good question. Sometimes they'll call this one K, and they'll call this one K minus 1. Right? So in other words, one will always be one greater than the other. You have to have it. Now, having said that, it's not necessarily just one term or the next. Sometimes, and that's what the second one, remember I said I was gonna do 3 with you guys, 2 and then the special one. The second one I'm gonna show you, sometimes you're gonna see that they have to give you 2 terms because each term depends on 2 previous terms, not just 1. You can actually do it even more. We're gonna stick to 2, we're not gonna start getting crazy here. Yeah.
So they're always gonna give you that A1 equals 4, like to
They
start
need
off?
to give you a first term. Without a first term, you can't start a recursively defined sequence. You need to have a starting point.
Okay.
Now, does it have to be the first term? No. They can give you the 5th term, then you go forwards. Now, once you go forward, well, if I know the 5th term, I can plug in the 5th term here to find the 4th term, and work backwards to get the beginning.
Mm.
Okay? Now, it's a little bit of extra work. It's not really more difficult. It's a little extra work because you're working backwards. But as long as you have something along the way and the formula, it doesn't matter. But you need to have at least 1 term.
Yeah, I get it.
Without the 1 term, you can't do a recursively defined sequence. Further.
Can you have negative terms?
Okay, good question. Technically, we can create situations with negative terms. When you write a sequence out, it doesn't make sense. Because what happens? When I start writing a sequence, I'm starting with a first term. Okay? So you'll never see the negative 4th term. Now, I can technically start going backwards and find terms backwards. But then what happens is, what you're doing is redefining it. So once the 4th term might not be the 12th term, because now I've got some negative terms, I'm gonna redefine them as first, second, third. Okay? So, good question. Yeah?
Would you ever have it depend on just 1 term, but it's the term like 2 spaces before it?
You can.
Yeah.
But if you do that, they'd have to give you 2 values.
Right.
Because if the 3rd one's dependent on the first one, well, when you get to the 4th one, it'd be dependent on the second one, so I'd have to know what the second one was.
Okay.
Now, having said that, this will be the next problem.
Uh,
So, by the way, remember, these continue. And by the way, sometimes people see patterns and they continue following the patterns, even if, once they're here, like, oh, I see a pattern, I don't have to keep going recursively. Great, you can always do that. There you go, let's do another recursive one. So I'm gonna do this. I'm gonna define the first 2 terms. I'm gonna define the first 2 terms. And what I'm gonna say this time is that a particular term is going to equal to the first one plus twice the next one. So what this is saying is this: to find a particular term, I'm going to look at both terms beforehand, and then put it into that particular recursive formula. So when k is 1, this would be the second term, and this would be the 3rd term. So in other words, if I want to find any particular term, I'm going to go back 2 terms, and I add that one to twice the one that's immediately before. So, when k is 1, this is 1, there's 2 to find the 3rd. So it's going to be 1 plus 2 times 2, which is 4 plus 1, which is 5. Good. So if I want to find the 4th term, when this is 4, this one's going to be 2n. So it's going to be the second term plus 2 times the 3rd term. What's the second term?
Second term is 2.
2 plus 2 times, what's the 3rd term?
5.
All right, so let's find the 5th term. So the 5th term is going to be the 3rd term plus twice the 4th term. So it's going to be 12, oh sorry, the 3rd term was 5 plus 2 times the 4th term, 4, which is, so this equals would be 1, 2, 5, 12. Questions, yeah.
I don't get like what happened after it A3 equals 5.
Once I get A3 equals 5, to get the fourth term, if this is 4, that means K is 2. So saying that's K2, so that's the second term plus 2 times the third term. So I take the second term, that'll be that, plus 2 times the third term, which is that. Yeah, these problems take a little long because we have to keep going back, referring to the previous term. So, I'm gonna go one more. If I wanna find the sixth term, if this is 6, that means that K equals 2 is 6, that means that K is 4. That means that I'm looking at the fourth term, plus 2 times. Well, when this is 4, this is 4 plus 1, it's the fifth term. So I tell you, find the fourth term. Fourth term is 12. Plus 2 times. Find the fifth term. The fifth term was 29. That'll be your answer. So you just have to keep going back through these terms and plugging into the third term. Okay? Questions? Oh.
Well, actually,
Yeah, I'm not gonna. Yeah.
this one, you wouldn't be able to figure out the formula from if you
There's
just got
no
this
real
number.
formula for this thing here.
Okay.
No. If someone can find it, great. I just made it up. So it's not like I can look and say, oh yeah, the formula. There might be one. I'm not gonna go through the trouble of doing it now. And if there is one, great. But for a lot of recursive formulas, there is not an actual, what we call an explicit formula. Explicit formulas are like the ones we saw on Wednesday. It said A n equals, that's what's called an explicitly defined formula. They'll tell you, here's a formula, plug in, go. Okay? This one I don't think is gonna give us.
Okay.
If they give you the numbers, can you find the formula for anything?
No, not always. Not always. Especially, this thing I know. All right, so I'm gonna go ahead and put up this thing called Fibonacci sequence. This here is probably the most famous of all the recursive formulas. Fibonacci sequence. Right?
How do you spell that?
I don't know how Fibonacci is spelled. It's called a Fibonacci sequence.
When I got the memo on the side.
Once I tell you how it works, you're never gonna forget how to get it. You know, you won't have to memorize it.
I'm not
Because it has recursive. Can anybody tell me how Fibonacci works? Valero?
You add the first number and the previous number.
There you go. All you have to do to get any one, you just add the previous number. To get each term, you add the previous 2 numbers. So notice, to get 2, I added 1 and 1. To get 3, it's 2 and 1. 5 is 2
Why is
plus
this
3.
famous?
3 plus 5 is 8. 5 8 is 13. ACS, 21, 34. So what would the next number be?
Really?
What would the next number be?
55.
55. If this is 55, the next one would be? You can do this forever. Okay, everybody see how easy it is? Very easy to create. Is there a formula for that? No. Now, and I want to talk a little bit about it because I did it in class. We have to what? 150, right?
Yeah.
Okay. The Fibonacci sequence. One of the really cool things about it is that if we were to take the ratio of any 2 terms and start creating a sequence of those ratios. So for instance, the ratio of this one over this one is 1. The ratio of this one over this one is 2. This one is 2. This is 3 halves, which is about 1.5. 5 thirds, which is about 1.666666. 8 fifths is 1.6. 13 eighths is 1.625. You start doing this. It's, all those ratios, little by little, start approaching a particular number. That particular number is about 1.615 around there. We have a name for that number. It's called the golden ratio. Has anybody ever heard of the golden ratio before? 1, 2, 3, 4 guys. Okay. Anybody who's ever read Dan Brown's the Da Vinci Code?
Nope.
That's a movie. Yeah. In the Da Vinci Code, they talk about Fibonacci sequence, and they talk about the significance of it. All right. Anybody know what a pentagram is?
Isn't that like what you use to summon Satan or something?
Yeah, the pentagram, this is what the pentagram looks like.
Oh, a star.
And a lot of people think that's some sort of devil sign. Actually, no, it's a mathematical symbol.
Math summon Satan.
Yeah, exactly.
That's why no one likes. That's why so many people don't like it.
Yeah, okay, so anyway. in this thing, when it's drawn properly, obviously I didn't draw it properly. It's a pretty cool thing. If I were to take the ratio of this part of the star to this little short part of the star, that ratio is the golden ratio. Now, if I were to then take this longer one, like for instance, go from here to here to this one here,
Also.
it also happens to give you the golden ratio. Now, the golden ratio happens naturally so much that it leads one to believe, how can everything be so precise? So let me give you an example of where we see the golden ratio. If you take everybody in this room and everybody does these measurements, and we take the average of all these ratios, you're gonna get the golden ratio. So you measure from here to here, and you measure from here to here. The longer one or the shorter one, the ratio is gonna be very close to the golden ratio. If we're gonna take everybody's here, it's gonna be everybody a little different because nobody here is obviously perfectly proportional. But if we take everybody's and we take the average, it goes out to the golden ratio. Upper part of the leg to the lower part of the leg, golden ratio. Torso to whole body, golden ratio. Hand to foot, golden ratio. From your chin to your nose, from your nose to your forehead, golden ratio. It is a commonly recurring thing. Now, it's not just in the body. If you guys ever seen, Da Vinci has that picture's got the pentagram, and inside, the other guy in the middle. And you'll notice that from here to here, shoulder to arm, broadness of the shoulders, you have your legs, all the ratios within the human body, he has them drawn within the pentagram. Okay? Now, it doesn't just happen on the human figure. It happens across nature. If you were to take a flower, pull it from the stem, and look at the thorns, you'll notice that the thorns are not all equally spaced. They're closer together, and then they get farther apart. If you start taking the ratios from one set of thorns to the next set, to the next set, it's the ratio. Wow. If you were to take a beehive, and you count the number of bees in the beehive, and this is a newly formed beehive before they all start to die out for whatever reason. Newly formed beehive. You take the number of bees one day, and then you go to the next day, and you take the number of bees the next day. You take that ratio, golden ratio.
What is the golden ratio?
About 1.615.
No, but like something to what?
It's just a ratio of two values. This is how, by the way, Fibonacci sequence, when he created it, is because he was seeing these things in nature. You see this here? He actually did this calculation by counting bees in a beehive. Starts with one, starts with the queen, and then the drone. Then the next day there was a third one. Then the next day there was 5 bees. Then the next day there was 8 bees. The next day was 13 bees. He calculated that. Fibonacci sequence came out perfectly from what was calculated in there.
So the Fibonacci sequence is like going
It goes on infinitely, but it's found everywhere. If you ever look at Da Vinci's paintings, a lot of them have all these different aspects, but one of the main things, he uses the golden ratio a lot. But the interesting thing is a lot of older paintings, before Fibonacci sequence was ever created, before the golden ratio was discovered, a lot of old paintings, when you start taking the ratio of parts and the proportions of things, they all happen to fall somehow or another with a golden ratio. So, the thing about that is, to me, and I look at this thing, and this is for me the proof that there is a God. I'm sorry. How can something so precise have landed everywhere and not be something that was planned? I'm sorry. Coincidences happen in this world, but not infinite coincidences. That's me. Some of you guys might say, no, they really do. There's a law, a greater law called chaos, that things just can't happen in the same way all the time. And yet it is. Within chaos, there's perfection. How does that happen? So anyway, somewhere in the Lambo decimal, there is a golden ratio hidden.
I saw the Lambo called.
Lambo?
He's referencing your made-up heartbeat.
Wait, what is the Lambo decimal?
One day we'll go over it. We have to wait till we can apply it.
I thought Lambo just made it up.
Listen, hey, we have 9 minutes, okay? I took some time to fool around with you guys a
It's
little
actually
bit,
8
joke
minutes. That's
around.
awkward.
We gotta
Albert,
finish.
it's 8.
Alright, so here we go. There's a couple other things we're gonna be talking about today. The first thing is what is called a factorial. The factorial. Now, when we talk about factorials, A factorial is when we take a number, and this was called factorial notation, we put a little exclamation point behind it. And when you put that with an exclamation point behind it,
You have
it's
to yell
read
it.
n factorial, not n! N factorial, okay?
Oh, so
Now,
unnecessary.
the way you calculate a factorial,
See, you
take
just
that
did what I
number,
did.
and you multiply by every one of the preceding integers until you work your way all the way back to
How do you see
one.
it through him playing?
So in other words, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Stop. You always stop at 1. Because if you get to 0, it's always going to be 0. That makes no sense. But anyway, that's the factorial. And I only have 7 minutes now, so now we have to actually focus and finish. If you have questions, ask me at the end of the period. That's a factorial. Now, one definition which we need to know before we get to this. 0 factorial is a special factorial that has a value. The value of 0 factorial is 1. So, let's briefly talk about the significance what a factorial is. Okay? So 5 factorial we just said is 5 times 4 times 3 times 2 times 1, right? Right. How does this work? There's 5 guys in this row, right? If I get these 5 guys, I say, all right, let's figure out how many different ways we can put them in order. So I have a first seat. So there's 5 of you. How many ways can I put somebody in the first seat?
5 times 4 times
There's
3.
5 guys, so 5 guys. Now how many guys are left? 4. So how many ways can I put somebody in the second seat? 4. And then?
3.
And then?
2.
And then?
1.
So when you have a factorial, what you're doing is you're trying to figure out the number of different ways you can order that set number of things you're collecting or putting in order. Yes.
Couldn't you just ignore 1 then when you're doing it?
Well, when you multiply, yeah, but technically it's part of the definition.
Okay.
Why? Because 1 factorial would be 1 way.
What are those 3 dots between the?
That you think continues until you get to 3, 2, 1. Because I didn't say what n was. I'm not, what if n was 97? I'm not about to go 97 all the way down, so I put the dot, showing you whatever n is, I'm gonna get to a point where it's eventually gonna go times 3 times 2 times 1 and so
So
on.
if the first n is 97, you have to start n minus 97.
I go 97, 96, 95, 94, 93, all the way down to 1.
That'd be an error.
Because it ends.
It's just skipping.
Okay, if I'm in 97, 97 minus 1 is 96. 97 minus 2 is 95. 97 minus 3 is 94. 97.
Blah, blah.
96.
When those are like all the possibilities.
And then
And it keeps going. I'm not gonna I can't put all the ends, so it'll keep going until you eventually get to times 3 times 2 times 1. Okay? So, yeah. Huh? Yes, but that's, we have to worry about other calculations, so hold on. Let me finish with everything first. Now, the reason 0 factorial is 1. If I have no things, how many different ways can you order nothing? 1 way. This is a conceptual thing. That's why it has to be written by definition. This is not something here that I can actually calculate. These I can calculate, this I can't, so we use the idea, the notion behind what it means to come up with a value. 0 factorial is 1, and we're going to see the value of that later.
Well, if you have nothing, doesn't it mean that you can't?
Technically,
put it in
that's like saying not choosing is still a choice.
It's a choice to not choose.
So I have nothing to choose from. Okay, well, then I'm not going to choose. By not choosing, I made a choice. So one choice I can make.
Nothing exists.
So, all right, now, let me finish because we only have 4 minutes. I took longer than I planned on doing the other stuff in the beginning. Joking around and stuff. So here we go. Now that's all sequences, and now we're going to talk about something called a series. Now when we talk about a series, this thing here
What?
is what is called sigma. This is the capital letter sigma. It's a Greek letter.
Not like my sigma.
Now whenever you see the capital letter sigma, sigma represents a sum. That means that anything I put behind it, I'm going to use to find a sum. Now what we do, what a series is, and this is something that people have to understand. Many times people confuse or they interchange the words sequence with series. A lot of times people look at a set of numbers and they go, oh, that's a series of numbers, and it's not. And I think we talked about it the other day. The difference between sequence and series, that in a series you take the sequence and you add them up. So when you see this symbol, they're telling you that if they give you a sequence, I'm not just going to list the numbers in the sequence, I'm going to actually add them up. Now, there's two types of sequences we have to worry about. One is what is called a finite sequence. Now, a finite sequence means, a finite series. A finite series means I'm only adding a finite number of values. This in here, this number here, is the first number we plug in. So if that's a 1, that means the first number we're going to plug in is 1. If that was a 3, the first number we'll plug in is 3. If that was a 0, and 0 is the lowest number you're going to see there, you can plug in a 0 first. That's the first number you plug in. Then you're going to plug in each ensuing value until you get to
The number on top.
this number here. This is the last number you plug in. Now notice something. Notice I didn't say that I'm plugging in this many numbers. You're not plugging in 5 numbers.
So you get,
5 is the last number you plug in. Now if I'm starting at 1, I will want to plug in 5. But if I started at 3, I'm not going to plug in a total of 5. I'm going to plug in 3, 4, and 5. I only plug in 3 numbers.
just to get.
Once I get those 3 values, what am I going to do with them?
Add them.
I'm gonna add them, because that's what this symbol means. So this thing here would be 2 times 1 is 2 plus 3 is 5. But then I'm going to plug in 2. So when I plug in 2, I'm going to get 4 times 2 is 8 plus 3 is 11. Then I'm going to plug in 3. 9 times 2 is 18 plus 3 is 21. Plug in 4. That'll give me 35. Plug in 5. That's going to give me 53. Now that total is the sum of that series. The finite series. So it's going to be 88, 93, 104, 125. Now this thing that we just found, this is what is called a partial sum. Now the reason it's called a partial sum is because the truth is that we can continue and extend this series. How far?
Infinity.
Infinitely. So since I'm only taking a part of the infinite series, we call it a partial sum. It's sum of part of the series. The part that I defined. Everybody see that?
Yeah.
Now, not all series are infinite. Are finite. Sometimes we're going to be dealing with what's called an infinite series. So, this is an example of an infinite series. Now, and I talked about this the other day. A lot of times people, they see an infinite series and actually have one written up, and automatically assume that the sum of that infinite series is going to be infinity. It won't always be. I'm going to go ahead and start writing this one out so you can see what it looks like. If I plug in 1 here, it's going to give me 0.3. If I plug in 2, it's going to give me 0.03. If I plug in 3, it's going to give me 9. Now, if you follow this long enough, what time is it going to be? What?
1/3.
1/3.
Oh.
0.33333. The 3's keep moving to a new place.
Oh.
This gives me 0.333333, which, as
Not
Dick said
surprising.
back there, this is 1/3. Now this is not a partial sum. This is an infinite sum. It's a sum of an infinite number of terms. Now, in this case, if I want infinitely, yes. Sometimes, most of the time, you're going to get an infinite sum.
If it's a whole number.
Sometimes it's going to be finite.
So if it's a whole number, it'll end up. If it was a whole number, it would always end up.
If they're whole numbers, it's either going to be something infinite or something that you can't calculate. And we'll talk about that more later. Your homework's on campus. Your homework's on campus. If it's not, I think it is all right. If it's not, I'm going to put it in.